and as a reviewer in several journals including MLJ, JAIR, Frontier, etc. Dr. Mayukh has completed his PhD in computer science with focus on artificial intelligence and machine learning from the University of Texas at Dallas, USA. His research and thesis work at the time centered around artificial intelligence model optimization and enhancement to mitigate the pitfalls of noisy inputs and sample bias using human artificial intelligence collaboration, especially in the context of graph structured data. This work was part of the exciting DARPA project, Communication with Computers, that he was involved with and is still an active interest. It also led to several publications in flagship conferences and journals such as KR, AAAI, AAMAS, SDM, KBS, Frontiers in Artificial Intelligence, etc. Just to clarify for those who are not aware, DARPA is the research funding division of US Defense. He completed his Masters of Science from Indiana University, Bloomington, USA. So I welcome Dr. Mayukh for this FDP, and I request him to share his valuable findings and thoughts to the participants. Dr. Mayukh.
Thank you for this very nice introduction. Today we plan to discuss something that I have worked on for the last few years, which is enabling AI in embedded devices. By embedded devices, I'll just share the slides in a minute. I just want to set up the stage for this. So embedded devices has a lot of definitions. But in this context, or at least for today, what we'll be focusing on is like, or
excuse me, sir.
By embedded device. Yeah.
Sir, the slide, you can share the slide, your slide. Is it possible?
Yes, just give me a second. I just want to set up the problem.
Yes.
Yeah, so embedded devices today that we are going to discuss essentially means that devices that where the chipsets are built in an embedded form, and the fact that the resources in those devices are constrained. So can you see my slides now?
Not now, sir. Yeah, it is visible now.
Okay. So today we are going to talk about AI in embedded devices. Yeah. So as you heard earlier, I am a part of Microsoft Research India. And before that, I used to work in Samsung Research, where I used to deal with these similar topics. And in Microsoft Research as well, I to some extent, I deal with these topics, right? So let us begin our journey through this. Yeah. Hello. Is anyone speaking? Hello. Is anyone speaking? I guess I can hear some voices.
Yeah. Please continue, sir.
Yeah. Okay. Yeah. So the plan for today is that since it's a long session, I will try to go a little bit slow, and I will pause in between. And though there is a Q&A session at the end, anybody is free to stop me at any point and ask for any clarification or whatever, because sometimes it's difficult for us to remember what to ask till the end. Or even we can lose the context or the passion for asking that question. Anyway, so I just want to make it clear that I'm open to taking questions in between. So that's it. Okay, so AI in embedded devices. So why are we interested in this problem? Before jumping into what happens in this area, let us look at what used to happen in this area, like from an industrial perspective. People when wanted to deal with AI models or build AI models for different use cases, build AI models or deploy AI models for different kinds of features, different kinds of intelligent features that they were building. There were like two main perspectives to it. One is people would end up using some kind of cloud infrastructure where the AI models and all the resources and the processing power is shared among various machines at various geographical locations connected via a logical cloud, right? So like if you wanted an intelligent feature or some app which does something cool, deploying AI. In such cases, all your AI model processing and inference and execution will happen on the cloud, and it will just exchange data and inference results with your device. On the other side, where was those kind of use cases or those kind of scenarios where such device and cloud was not there, but you had this huge farm of servers with very powerful processing units, right? And whatever AI related stuff you wanted to do, for example, you want to do meteorological predictions, you want to predict the weather, you want to predict how ocean currents will look like tomorrow, or you want to predict, for example, you have this huge data and from which you want to predict or make user recommendations, such as you get in Netflix or something, right? So in those cases, they have these huge farms of servers, and AI models are huge, and they process large amounts of data, and they're housed in these large server farms. So, but imagine like if you are only restricted to these two cases, cloud AI and AI on these large server infrastructures, there are dangers to it. One, on the cloud side, there are dangers like there could be failure of the network, failure of the internet, where sending data and receiving inference results from the cloud becomes a problem, or there may be failure inside nodes of the cloud where your processing was halfway done and the predictions it made are not correct. That can be the case, though people are working on it, but these are some of the problems that does exist till now, right? And if you are using huge server farms to do huge things, then I guess like in some cases it is indispensable. You have to use these huge infrastructures. But in many cases, for small applications, you don't need these huge infrastructures. So to have these huge infrastructures, you have to have huge investments and a lot of dollars or a lot of money is spent, right? So there is a paradigm shift, as in there is a shift in trend where people are thinking more towards shifting the load of intelligent computations towards smaller devices. For example, if you have a phone and your phone is connected to your TV, your smartwatch, your car, etc., right? So instead of for every earlier, what used to happen is for every intelligent decision you made on the phone, for example, you want to predict what this picture that you have clicked, what this picture is. For example, you want to predict whether this is a scenery. Based on that, you'll change the brightness or the contrast or whatever, right? That prediction, if that prediction problem is sent to the cloud, it'll take some time. There'll be some latency in going to the sending the data to the cloud, getting the results back, etc., etc., and you'll be tired in between. More important is, for example, cars, right? So you have like self-driven cars, or even normal cars today have computers on board that make a lot of predictions. For example, there are automatic accident detection protocols inside those cars, right? So how does those cars detect that? Is it like a simple sensor? Not really. Like it's not just simple sensors. Like there's sensor data coming in, and then it needs to be processed. Some inference needs to be made. There is some model that there is some AI model that is there which predicts something based on that data. For example, it predicts whether an accident is going to happen or not going to happen. That prediction has to be made. So there is some model that is there which makes those predictions. So if it was in the cloud and your car is sending data to the cloud and it is getting back the results at some point and then taking the decision as to whether an accident is going to happen, whether automatic brakes should be applied or not. If that decision used to happen that way, then obviously you'll have thousands of accidents, or you'll not get the alert in time, right? So in such cases, processing it on the computer that is onboarded on your car makes more sense. So there are many reasons for this paradigm shift, which is written on the right hand side, right? There's privacy, like some data you do not need to share with the cloud, right? There's reliability, as I was saying, right? Your results need to be reliable and be on time, right? And low latency and efficient use of network bandwidth. Like if you're using network bandwidth just to transfer data across the cloud and results of inference across the cloud, then that's not going to be good for us, right? We need to use the network bandwidth in important situations where some top level or some big decision needs to be made, and that big model resides in the cloud. So maybe for example, if your car needs a tune up right now or not, right? So that decision can be made via cloud. But your accident alerting or accident detection is not something that you want your cloud to be involved in, right? So that's why there is this shift in trend or paradigm. Okay, so I've spent a lot of time on motivating why we are doing this today. Now, the idea is that I'll go through some of the things that are involved in making our AI possible on such small resource constrained embedded devices, right? And at the end of 1 hour, we'll take a small break and I'll pause for maybe 5 minutes to get your thoughts together. Then we'll look at a case study, right? So this is how it'll go. The first four things are I'll talk about some of the facets of AI as such. In pictures, I like pictures, so you'll see a lot of pictures in my slides. I don't like too much equations and stuff, right? And then I will talk about the challenges of AI in this embedded space. Then we'll talk about how to make models lighter or make efficient inference for AI that is deployed in these embedded devices. And then we'll look at something called neural architecture search, which is comparatively new and I think will be quite cool, which is also related to making models lighter, right? And then we'll do a case study as to how these neural architecture search methods come into play in case of embedded AI, right? And then we'll wind up. So that's the plan. So AI and its many faces. So let us go there. So what exactly is an AI model? I'm going through these topics because you'll see that if you remember these few concepts or these few key ideas, then the later slides will be easier for us to understand, right? So there is a huge hype around AI. Like everybody wants to do AI. Every company wants to have AI-driven solutions. You'll see news on LinkedIn. You'll see news on Facebook. Like everyone, like even the smallest garment store is trying to deploy AI in some way. It sounds hilarious. It is hilarious because some people do not understand what AI entails, right? What an AI model is. And also there is this notion that I want to dispel today before going further. That like some people think deep learning is something else, AI is something else, machine learning is something else. That is not true. If you look at this small diagram in the corner of the slide, you'll see that AI is the outer shell. Inside that lies machine learning, because AI involves a lot of methods, learning and non-learning methods. So all the learning methods fall inside machine learning. And inside machine learning, a particular way to do machine learning is deep learning. So that should be clear to all of us before all of us are excited about deep learning or non-deep learning or whatever, right? So what is an AI model? There are many AI models in our space. There are simple linear regression models. There are decision trees. There are support vector machines. There are Bayesian networks. There are deep models, convolution neural networks, which are deep models, transformer networks, which are deep models. There are statistical relational models that work on abstract data or graphical data, whatever, right? So there are many kinds of models. But what exactly is a model? A model can be thought of in simple terms. It can be thought of as some kind of transformation functions, right? So you have a bunch of observations which we call data. It is then that data or that observation can then be transformed into something, some value, right? It could be some value, yes or no, or it could be some value which is a number, right? And so the task of this transformation function is when a new observation is there or new data point. So that new data point is can when then fed into the transformation function will give us a prediction. That is, it will give us a value. So that value will then mean something to us. It may mean that it is predicting whether it something is going to happen, yes or no, or it can be that it is predicting some number, as in like what is the relation between this variable and that variable. So if this variable has value 5, that variable will have value 10, right? So that is what like no matter who is doing what, this is what an AI model is, like no matter what kind of model that is, right? So that we need to remember. Okay. So given that, though I'm saying that everything is a transformation function, I would also like to add that there is no free lunch. Like different things require us to do different things, right? So for example, there are traditional machine learning models where you get the data in the form of tables, as in there are columns and each column has values and you have multiple rows. So that is tabular data. So if you have tabular data, you have these simple machine learning models called linear regression, which is a regression model. That means it predicts a numerical value. Or you have decision trees, which predicts categorical values, as in like classes, yes or no, or high, low, medium, etc. Right? And also you have support vector machines, which can either be regression models or classification models. Right? Sorry. So and then there is graph structured data, which is called network or relational data. For that, you have a bunch of different models, right? You have graph convolutional networks. You have statistical relational models. So those are called SRLs. Then comes the advent of deep models, which people are so excited about. So for textual data, there are different kinds of deep models. About a few years ago, people were excited about sequential models such as LSTMs, etc. Right? These days, people are excited about transformer models, which looks at each word in a sentence and assigns some kind of attention to those words, or some kind of importance to different words in a sentence, such that whatever sentence or whatever text you predict next will be based on whatever importance you gave to the previous text, right? And then there are like computer vision models, where such as convolutional neural networks, CNN architectures, which does image classification or object detection on images, right? Even there, you have two different types of models. One is object detection classification models. Another one is image segmentation, where you want to find out regions in an image, right? You want to segment regions in an image, which also is similar, but not exactly. It needs some kind of a decoder architecture in order to give you actual segments in the image. So that's why I'm saying there's no free lunch. Then there is this matter of shallow versus deep learning. So deep learning is something people are too excited about these days, right? But both in academia and in the industry. Like everybody wants to do deep learning because we think deep learning is the answer to all our problems, which is not true at all, right? So, but the sad fact is I'll discuss a lot about these deep learning things today. But I want to make this clear that normal machine learning is this. Like when you look at the picture above, when you look at the picture on the top, you'll see that normal machine learning is two steps. You implement some kind of algorithm in order to extract important features from the data. Features is description of different things, right? Either the features could be the columns in your data. For example, if your data has columns like age, sex, or whether you're a first year student or second year student or you're a faculty, etc. Right? So these could be features, or you could have more complex features, right? If for example, if a faculty is advising a student, then that faculty is the advisor of a student. So whether the faculty is an advisor or not could be a feature, right? So that would be extracted as a complex feature from your data. So you write those algorithms, and your data and those extra features will be extracted from your data. And then using those normal features and the complex features, you build a nice model for classification or regression, whatever, right? And so even in vision, right? So this example is about vision. So if you had a picture of a car, right? So in normal machine learning or vision that happened, computer vision that happened like 5 or 6 years ago, there what used to happen is that looking at the picture would then pass through some parsing algorithm or some feature extraction algorithm, where you would like some kind of signal transformation algorithms would extract features such as whether there is a curvature, where there are two circles, which could mean if there are wheels or not, right? So all these features would come in, and then you'll build a machine learning model which would tell you whether it's a car, right? So that's how it used to happen. Now, what deep learning does is it encompasses this feature extraction and the modeling together. Like, so you just feed the normal raw data, and there are many layers in the deep learning model, which progressively squeezes out important features from the model. So basically, you are combining, or you are squeezing together the feature extraction and the classification or the modeling step together. So that is what deep learning is.
Sir Mayukh Das, just
Yeah.
to interrupt, please. So our Professor Sancheti sir is there from AICTE for evaluating this session. So I
Sure.
welcome Professor Sancheti sir. And just for, let's say, to introduce him to the participants as well as speakers and other gathering. So now over to you, sir. Please, sir. You can unmute first and then introduce.
No, no, I don't want to introduce myself. That's not required. I just want to be a participant here along with some of you. Please continue the session. I don't want to interrupt you, except for letting you know that I was the former Vice Chancellor at the Manipal University, Jaipur itself, almost as a founder Vice Chancellor. So I'm happy to join you. So Mr. Mayukh Das, please continue. I'm very happy to see you. I'm told that you are from Bangalore, from Microsoft side, talking about the machine learning and other concepts. So please continue. Thank you so much.
Yes. Yeah. It's very nice to meet you virtually. Yeah, we can talk. If you have any questions, do stop me anywhere, and I'll answer. Yeah.
Sure. Thank you.
Yeah.
Thank you. Thank you so much. Over to you, sir.
Thank you.
Mayukh Das, sir.
Yeah. So moving on. So again, another two sides of this AI machine learning is that there is something called learning and inference, right? Yeah. Somebody is speaking. Yeah. Sorry. So learning and inference, right? So learning is the fact that you have a bunch of training samples, and you are actually building the model, as in you're training the model such that at some point, given a new observation, your model will be predict whether that observation is, for example, if it's a car or not a car, or if it's an animal or not an animal, if it's a dog or if it's a cat, right? So, but that doesn't happen at the first step, right? You have a bunch of data of different cats and dogs and cars, etc., and your model it adjusts its own parameters, its own structure or its own parameters in such a way that it learns, or the function is kind of finalized into the form where, given any new sample, it will be able to predict whatever you want it to predict. So that is learning, right? So for example, in deep learning happens by something called You have heard about it. It's called backpropagation. So there you define the gradients between your predicted value and your true data, and those gradients are propagated back across the deep learning, across the deep model, in order to update the parameters or the weights, right? So it's not super important right now, but these concepts needs to be there with us in order to understand what happened, what I'll talk about later, right? And then there is inference. Inference is nothing like when your model has been trained, it's in its final form. You can give it one or a few more samples which was not there in your training data, and your already prepared model will now be able to predict which class it belongs to, or predict some number that you wanted to predict, right? So that is what inference is. And finally, another phase of AI is structure and parameters, right? We need to understand that most models can be thought of as having two parts. Most AI models can be thought of as having two parts. One is a structure, and another is parameters. Structure is what the shape of that transformation function looks like, and parameters is the coefficients of that function. In simple language, you can think about like that, right? For example, if you have a linear or a nonlinear regression function, right? For example, if you have a polynomial regression function or linear regression function, the linearity or the way the polynomial is defined. For example, if this I on top of x, right? So that is the highest power of that polynomial. So if that power defines the structure of that function, right? For example, if the power is 3, then it's a cubic polynomial, right? So that will have a different shape, right? As opposed to linear, which is where the max power is 1, right? So in that case, that's a linear function. So that's the shape of the function or the structure of the function. And so I have marked it wrongly. This I is the structure, and the parameters are the coefficients. So for every power of x, there is a coefficient. So these are parameters because these need to be adjusted. So once you decide the structure of your function, that is fixed, right? Once you decide whether I'll model this problem as a quadratic polynomial. So that structure is fixed. You can't change it after you have decided it, right? So what you can change from the training data is the coefficients, right? You can change the slope of the line in some sense. So if you're changing the slope of the line, that means your coefficients are changing. So you change the slope of the line in order to fit the points that lie in that space. So that is what linear regression is. So that's the structure. So similarly, in many other models, structure is something that how the shape of the function looks like. For example, in Bayesian networks, the structure is the dependencies between the variables. That is the structure. And the values of the probabilities or the conditional probabilities because of those dependencies are the parameters. Similarly, in deep models, right? In deep models, these like how many neurons are there in this layer? How many layers are there? Right? How to connect those neurons? These are essentially the structures, and the weights of those interconnections basically are the parameters. So this is what is meant by structure and parameters. So now let us take a pause for a few seconds and tell me, like, so what do we? I encourage answers here. If nobody answers, then I'll move on. But what do we do with AI models on devices, right? So if we have devices, what are we doing with AI models? Are we learning something, or are we doing inference? So that's my question here. Anybody can answer if you have the answer.
Participants, could you please ask a question or reply to the question?
Yeah. So okay. Let's move on. So maybe people are not comfortable yet. So we are interested in performing inference. So when we deploy AI models on these devices, we essentially want to perform inference, as in the model we have learned somewhere else, and we deploy that AI model on devices such that when new things or new observation comes from the sensors on our devices, sensors or camera or whatever, the model will perform inference and tell us something. For example, we click one photo and the scene optimizer model in our, so for example, in our Samsung phones, will perform inference on that clicked photo and will enhance it in some way based on what that scene is. For example, that scene is like a mountain and stuff. So it will enhance in such a way. Or if it's a portrait, it will enhance in some other way, right? So that's what we do in devices. That's what we are interested in. There is some learning that happens in some scenarios or some use cases, but that is not our concern today. And that is also rudimentary in nature. Like learning, full-blown learning does not happen on devices yet. So what is the big deal about these, about doing inference on devices, right? So the big deal is that there are many scenarios and there are many types of models. How do we store all those types of models in one device, right? And there could be many types of data. There is image data, there is text, there is speech, there is audio, there is video, right? So again, there are many types of models that are going to come because of the types of data, right? And finally, what is most important, I have double starred this, is the constrained resources that we have on devices, because it's an embedded architecture. You can't extend those. In some cases, you can attach memory or a storage chip, extendable storage. There in some phones, but that's only for storage. Like you can't extend the RAM, you can't extend the ROM, you can't extend the processing power. So these are embedded chipsets, right? So resources are limited. That is very important. So now moving on to challenges of AI in the embedded space, right? So this is the main meat of the talk. For this long, I have been trying to motivate why we are trying to do all this, right? Or what AI means in case of embedded systems. What is embedded AI? Like we have intelligent mobile devices. It may be smartphones, it may be our smart TVs, it may be smart watches, it may be IoT setups, right? Or it may be some smart home setup where you have multiple sensors and those sensors will take some intelligent decisions at certain point, right? So you have all of these kind of devices, and when machine learning models are deployed on those devices, it becomes embedded AI. So there are various kinds of these mobile applications that you want to perform, and that leads to various AI models. There are many new kinds of tasks that needs to happen. That, for example, you need to predict what this, for example, this picture, right? You need to predict what this is. For example, this is a shoe, or you need your phone to take you to the shopping link, or take you to Amazon automatically when you click on a shoe, right? So that you can buy that shoe. So people want to do that these days. Or even like text prediction on your Samsung keyboard or something like that, right? So all these tasks are coming up one by one. Then these tasks are getting more complex. We'll see that later, right? And then the devices themselves are evolving. The chipsets are evolving. Like then I was in Samsung, so I'll talk about Samsung. Like when I joined, we were in like S11 or something, S12. I don't know. Like then they changed. Then they made it S20 to align with the 2020, 2021, whatever. Right. So previously they had GPUs on chipsets. Then we also have GPUs now and NPUs, right? So we'll talk about those things later. But mainly, like everything, the hardware is also evolving, and so will the models, AI models. So that is embedded AI. So let us look at some of the challenges that we will encounter in case of embedded AI. So the story of processing units, right? So as you can understand, right? So we have our processors are changing, as in like our focus on which processor to use in order to do AI on devices. That focus is changing. Previously, everything used to happen on the CPU that was provided in your chipset, right? And at that time, CPUs as you can understand, CPUs have the highest instruction set generality, as in most things, or rather all things, all kinds of computation is possible on CPU. They may not be optimized, they may not happen the fastest, but they will happen on GPU, on CPU, right? Then we adopted GPUs to deploy AI models, to deploy heavy AI models, because we think that GPUs are good with matrix computations or numerical computations. That's why when we deploy models that are numerical, that are heavy in numerical computations, we migrated towards GPUs. But as you can understand, GPUs can do certain things, but generality is less. It cannot do certain other things, right? And then finally, these days in Qualcomm chipsets or in Samsung chipsets, etc., you have something called NPU or Neural Processing Unit or AIP or AI Processing Unit. Or Google has something come up with something called TPU, Tensor Processing Unit, which Google is calling Tensor because they can do that, because Tensor is a three-dimensional or multi-dimensional matrix, and they have no care for what other people think, and they're calling their processor Tensor, which is great, but it's there, right? So what happens in that is that these processors are highly optimized for doing tensor computations, tensor manipulations, but they have a catch. In some cases, in many NPUs or TPUs, processing can be fast only if the numbers are integers in some sense, right? So integer numbers are processed fast, but if the numbers are not non-integers, they can become slow, right? So this is what happens. So what is this question mark? This question mark is this particular curve, the reverse curve, is basically the curve of our tasks, right? Our tasks are slowly becoming more and more complex, and we require more and more instruction set generality. So we have to do something in between, right? Then there is the story of devices, right? There are many kinds of devices. You have devices which are phones, right? You have different generations of phones, different companies of phones, right? Then you have like smaller devices that goes on your wrist, or smartwatches. Then to these days, TVs are smart. Like many of the intelligent processing happens inside the TV instead of cloud, right? Even IoT devices, as I was saying, like many of the computations will happen inside your sensor. For example, this door camera that you're seeing, right? So that's what. Even today we have smart fridge. Like so many things are many computations are happening inside the fridge computer itself, right? But what's happening is that hardware is changing like every quarter in some sense. Though all of them can be considered as resource constrained devices, hardware itself required for these computations, they are changing in every quarter. And then there is the story of intelligent features, the features that we are actually happy with these days. So if you look at the left, we were happy with slide scene optimization like few years ago, or very dumb very dumb autocorrect suggestion. A few years ago, we were happy with that. We were happy with taking the suggestion or not taking the suggestion. But later on, our demands increased. We wanted our phone to take us automatically to the shopping website when I click a photo of the shoe, or when I crop the photo of the shoe, right? And then there's something called shot suggestion. It's there in Samsung. So it will suggest you the best shot basically. Then there is night mode correction, etc. And furthermore, what we want more things, right? So there are computers on cars now, right? So that is an even more complex task. These sensors are looking at road signs, inferring what these road signs look like at real time, mind you, right? And then inferring what this road sign might mean given the type of the road that the car is driving on, right? So all of these decision making is happening on the go. So that's why it's an even more complex task. And also we want our email clients to predict whole sentences for us. So that's a more complex task, right? So that way the intelligent features that we are happy with, that space or that landscape is also changing. And then there are software accelerators, right? So so what are software accelerators? This is something that we have to understand before we move on. So, so our phones, we have our phones, we have different kinds of these embedded devices that I have been talking about, right? But is it possible to directly take an AI model? For example, you learn a CNN or you learn a Bayesian network, and you want to directly make it work on your phone. Does that happen so easily? No, there are many considerations that needs to be taken. How the data needs to be processed inside your chipset. How it will access the different compute units like GPUs and CPUs, etc. Right? How it will transfer data between the different software stack of your Android installation or even in Apple, whatever. Right? So all of these are very critical decisions, and it might become very complex for an AI expert, such as, for example, me or somebody else who's working on an AI application. Such people, it might be difficult for us to take those system level or firmware level decisions, right? So what happens is that many companies offer these software stacks, which are called accelerators or neural network accelerators or neural accelerators, that make life easy for people who are trying to build AI neural models and deploy on devices. So they just put the model somewhere in some specified location or some, and like write some one or two subroutines in order to use those models, and rest is taken care of by the software stack. For example, there is Android NN by Google for Google phones, or even Android NN is present in normal Androids, in other Android phones as well. But some companies choose to use or not to use it, right? Then there is SNP by Qualcomm. If your phone is using a Qualcomm chipset, then Qualcomm itself provides this software stack, which makes easy for deployment of AI models on the devices. Then there is Samsung has something called Samsung Neural APK, and Apple has something called Core ML. So these are similar software stacks. So while they're trying to make your life easier, they also create difficulties for you. For example, with some models or some functions in your deep learning model works well in some of the software accelerators, or it does not work well in some other software accelerator. So you may have to slightly alter your model to adapt it to the software accelerator that you are using, right? So that is one thing. So now we are at the end of this section. Uh, so the question, the haunting question is that, so now that we know all of these things, so what really are the bottlenecks in running DNNs or running deep models or AI models on devices, right? Uh, so these are the bottlenecks. So there is inference latency, as in like when you're trying to we'll talk about this in a minute. So what happens is that if you deploy a model, or if you have an AI model that works on your phone, for example, that is doing scene optimization, if it takes, for example, 2-3 minutes to finally optimize your scene, you lose interest in clicking that photograph as a whole, right? So it has to have very low latency. Then memory consumption. For example, if the scene optimizer model in your phone, right, is consuming a lot of memory, it's taking up, for example, 60% of the RAM, all your other apps or all your other functions will slow down. For example, when you click on the back button, you'll see that the response is very slow because your scene optimizer model is still working, or it has taken up a lot of memory, right? And then there is power usage. For example, if you push the models to sometimes to have low latency, it can sometimes take up more power. Like it'll take up more. It'll try to process more instructions per minute, and then it will consume more power. Your battery will become heated, or your power will fall very fast, right? So what is responsible for this power usage? For example, your model has such a representation that is using large floating point numbers or flushing the register too many times, right? So in such cases, power usage goes up, right? So these are the factors. So what we will talk about today, in order to make AI possible on devices or on mobile devices, is how to make models lighter for efficient inference on devices. So efficiency includes low memory. Efficiency includes how to make models faster or make them run faster, make them lighter, make them consume less or reasonable amount of power, increase their throughput, etc. So all of these comes under making models lighter. So if you remember, there are two parts to any model, even including deep models, right? So one is architecture or structure. Structure, I have called architecture as structure as architecture in case of deep models. It's called architecture, and then there is parameters. So for model optimization, there are many methods, and they can broadly be classified under these two sections, right? Some methods are trying to alter the architecture of the deep model such that they become lighter. And some models are trying to squeeze or compress the parameters in such a way that computation becomes faster, memory consumption becomes less, etc. So I'll start from the bottom and go to the top. That will be our cycle in looking at these methods. And finally, we'll focus more on NAS. That's why it's written in big bold letters, right? So before going there, what I want to mention is that though I have divided it into these two parts, it's not always true that the distinction is absolutely critical. As in, sometimes it may so happen that some models are doing, in some sense, they are changing the architecture as well as they're compressing the weights or the parameters, right? So both can happen. So what do we need to remember before jumping into all these methods? We need to remember is that we need to handle complexity of computation. We need to handle the number of parameters that your model has, which will contribute to how much memory it takes. We need to take care of the bottlenecks inside the model, as in, for example, a new data point, right? A new sample is flowing through your model in order to transform and then give you a prediction or classification. If that is the case, then your model can have some transformation functions inside it, which is taking more time than the others. Then that particular thing becomes a bottleneck. And then platform support, as in whether, as I was talking about it, right? In some cases, some operations inside the deep model are supported by some software stack, or is supported by, for example, NPU does not support floating point computations yet, right? Maybe tomorrow they will, but yet they do not, right? So these platform support also becomes important. And finally, how models or functions are represented. So we will start with the last point, which is MLIR. So MLIR means machine learning intermediate representation. So ideally, this should be deep learning intermediate representation, because normal machine learning with shallow models, we don't care about all these things because they work normally well on CPUs itself. But in case of deploying deep models, this MLIR becomes important. Why? Because as I showed you, so I don't know if all of you have, but there are things called TensorFlow, PyTorch. These are basically frameworks provided by Google or Facebook, using which people can code and develop deep learning models, right? And finally, when the deep models are learned, they are encoded. The model itself has to be encoded in some form, right? For example, linear regression. Linear regression does not need too much encoding as such. If you somehow indicate what is the highest power of your polynomial, and then you indicate as an array of coefficients, you are done, right? But deep models, you can understand, it's like a bunch of millions of neurons and parameters, right? So they need some kind of encoding. So there are these two famous frameworks called TensorFlow and PyTorch. So the people can develop deep models in these frameworks, and they have their own encodings as well. So when the deep models are learned, either they're encoded in TensorFlow form or they're encoded in PyTorch form. And there is something called ONNX it's an open source, it's an open exchange format basically. So those things are there, right? So models are learned in these encodings. Then there are your software accelerators, which kind of require your model to be tuned in such a way that it works with those software accelerators that I showed you. Then there are hardware accelerators built by different companies for particularly your chipsets, right? And then there is mobile hardware, which contains different kind of compute units such as GPU, CPU, whatever, right? And so this becomes a difficult deal, and in the entire production cycle, you learning a model to actually making it proper or making it tuned for the particular software accelerator, then converting it into a form which is well suited for the hardware accelerators, and then finally running on mobile hardware. So all of these companies together, like AMD, ARM, Google, Qualcomm, the Samsung, all of these companies together have come together to develop this internal representation, which will take away the pain of all these conversions and tuning and will be represented in a single form, which, as you can understand, will automatically make the models much faster and much lighter. So that's one thing. Second thing we come to is quantization. Quantization, as you can understand, it comes from signal processing, right? You understand that a continuous signal can be quantized into some quanta that you decide, right? So similar things can happen in deep models as well. In deep models, all these coefficients or parameters or weights are usually in floating point or decimal places, some decimal places with some precision, right? It can be quantized to reduce the precision of those decimal places or of those floating point numbers, and that will reduce the computation overhead as well. It will reduce the register length that is required to process those numbers, the memory that is required to store the entire set of parameters, right? That is quantization. As I told you, like quantization is required because different kinds of compute units have different requirements. For example, GPU works in FP16 but is not optimized to and NPUs or TPUs do not work with floating point at all, right? Till now. Sorry. Yeah. So there are different kinds of quantization methods, which I'll not go into detail because we are trying to keep this talk within time. So for example, there's post-training quantization, as in you have already trained a model, you have already learned all the weights that can be learned. Then you give it to a quantizer and it takes those weights and reduces the precision in such a way that the memory requirement or the amount of or the size of the parameter space is reduced, but the accuracy is maintained. That's the idea of quantization, right? So there are two types of post-training quantization: data-free, data-aware. I'll not go into detail. You can understand by the name, right? And then there is quantization-aware training, as in while you are training the model, you train it in such a way that the final model your training algorithm outputs is a quantized model in itself. Then there is quantization via knowledge distillation. I'll come to what knowledge distillation is. You'll understand that. And finally, there is binarization, as in you aggressively quantize in such a way that you make the weights now only have two choices. For example, 0 or 1 or true or false. That is very difficult, as in making your weight 0 or 1, just two numbers, and yet maintain the accuracy that you got with full floating point precision is a difficult task, and it's an ongoing research. So that's it. Then we come to knowledge distillation. That is also a part that I showed you, right? So knowledge distillation is, yeah, please go ahead.
అప్లోడింగ్ ఆప్షన్ లేదు మిగతా పేపర్స్ కానీ ఈ లోపు వాళ్ళే మాడిఫై చేసి పంపించు.
Hello, I can't understand your question. Hello.
Lata, your voice is breaking. Please speak clear.
Hello. Okay, I'll carry on for now. If you can re-ask the question when your network is okay. Yeah. So yeah, moving on to knowledge distillation. Knowledge distillation is basically, as I have mentioned in this statement, right? If you are tasting a Gordon Ramsay's recipe, but you do not have the recipe, so you recreate a simpler homemade one which tastes kind of similar to that, right? So that is what you have a big neural model, and you want to learn a smaller one to save computation as well as save time. So that So that is done via using the big network as a teacher model, and then learning your smaller model as a student model. So basically what happens is, if you look on the right, you'll see that the big teacher model gives some predictions. So that predictions become your extra data labels. And then you have a small set of true labels as well from your data. And you use both of them in order to retrain the small student model. That way you hope to reach the accuracy of somewhere close to the accuracy of the big model, while keeping your model small. So that is what distillation is. And there are different kinds of distillation. As you can see that you can do an online distillation where teacher and student are trained at the same time. You can do self distillation where teacher and student are the same model, as in you are squeezing the same model on top of it. You're not learning a separate model. So that is knowledge distillation. Then there is pruning or sparsification, which is as the name suggests, right? There is as in you are trying to get rid of some of the interconnections between the neurons in a deep model, so that your parameter space is reduced. So for example, there is unstructured pruning, which is like basically you have a threshold and you train in such a way that that some of your weights are moved towards zero, and then you just exclude the weights that are close to zero, right? So that way, that is called unstructured pruning, because there is no structure to which of the weights will be pruned. It's just based on some threshold. Then there is structured pruning, where for example, in CNNs, which are used for computer vision, right? So you have these convolutional filters, which and in a certain layer you have more than one filters, which are called channels. So if you want to reduce the number of channels, as in you want to get rid of some number of filters inside one layer, right? So that means there is a structure to what you're getting rid to. So that is structured pruning. That's pruning. Yeah, so that's it. Then there is I was talking about decomposition, right? So that is not too difficult to understand. Decomposition is like if you're aware of things like singular value decomposition or something, right? So you can understand that given a tensor, there are ways in which the tensor can be decomposed into two or more parts, right? So similar to that, you can decompose the parameter space. For example, this huge tensor or multiple tensors of weights that you have for deep models in such a way that your computation becomes easier and faster. For example, this is one example. If you know this is a mobile net. This is something called MobileNet V2. It's a very famous deep model that is used for image classification in mobile phones, right? So many of the camera applications use MobileNet V2. Why? Because they are the first one who made this model run faster or made this model lighter by decomposing a three-dimensional convolution, which is a tensor, into two steps of tensors. As in, like, first there is something called a depthwise convolution, as in you convolve across only within a single channel, right? And then you convolve with one unit across all channels, right? So it becomes two steps. Instead of doing this 3D convolutions across 5 cross 5 cross 3, you are doing first 5 cross 5 separately for all the channels. And then when that is done, in the next step, you are doing 1 cross 1 across 3 for all the three channels. So that reduces your computations like a huge amount, and that makes the models run very fast. So that is what decomposition means. And finally, so we are there. So finally, there is something called neural architecture search. So now that we have talked about all these making models lighter, all these ways of making models lighter, all of these require some amount of expert intervention, right? An AI expert needs to understand what needs to be done where, how much pruning needs to be done, what kind of pruning needs to be done, which channels needs to be excluded. how to judge whether a channel needs to be excluded or not, whether a channel needs to be pruned or not. So all these judgments, all these decisions need to be done by the AI expert. And sometimes these decisions can fail. Then we go back to the drawing board and we figure out some other way to do this, right? So to reduce all of that pain, there is something called neural architecture search. We build an automated intelligent system which can intelligently decide what to do in order to change or alter a model to fit your need, right? So I'm saying this in a very general way, but we'll see later how it fits into embedded AI. But this is what happens that basically there's a search space. Search space is what you want to do with your model. So different kind of options that you have in order to make your model optimal. Then you have a strategy for searching through that space. And there is some kind of performance evaluator, which evaluates each candidate that you do after taking a decision. Then that performance is given back to your search strategy module, which sees whether whether these changes that it has made in this step are they good or not. Could they judges the quality of the decision, and then finally decides to whether to accept or discard that change. Right? So that is what neural architecture search is. So anyway, so I think a lot of information has been pushed into your head. So you can just take a screenshot of this particular slide. Basically, this will give you an idea of the different methods in which models are optimized and the different categories of methods. Right? So this is this. I wanted to flash this. So yeah, I promised you guys a break, but I think we are kind of a bit of a time crunch. So I'll continue and give a break in a few minutes later. Before moving on to the case study about neural architecture search on embedded AI, let us first understand what neural architecture search entails or how it works, what it means, right? To motivate you, you can understand. You look at this plot, right? So you can see that before around 2017 or 2018, rather early 2018, you can see that most of the important models in computer vision were designed by experts, by machine learning experts, based on what is required in that task, how much fast that model needs to be, etc. Right? But after 2018, you can see all the advancement that is coming in terms of faster, more accurate models is designed by AutoML or neural architecture search. NAS and AutoML is an interchangeable name. Google calls it AutoML, and the other rest of the world calls it neural architecture search. Anyway, so and this graph continues. It's not plotted anymore. This graph is from 2 years ago. So the rest of the plot is not here. So it continues beyond these limits of the plot, right? So many of the recent architectures are also designed by AutoML. So what exactly is NAS? So before we delve into that, let us go back few steps. First, I want to mention is that these deep models are non-probabilistic. There is no joint distribution. The joint distribution of all the model parameters, joint probability distribution. Distributions means probability distribution. I assume everybody of you know that. The joint probability distribution of all the model parameters and the data together, that does not exist. There is no such notion in deep models, except for some deep models which are called Bayesian deep models that are being researched now. But in general, deep models do not have that notion. Unlike some of the probabilistic models that we have seen in our lives, such as Bayesian networks, right? What are Bayesian networks? This is a very famous Bayesian network where about alarm, burglary, earthquake, whether John calls or Mary calls, hearing that alarm, right? So there exists a joint distribution of all the random variables and the data, and the structure, and this joint distribution is actually factorizable if you understand Bayesian networks. I'm not going into detail because that's not today's topic, but it is factorizable in such a way based on what are the dependencies among the random variables. And that factorization actually gives us the true structure of that Bayesian network. But in deep models are essentially stacked transformation functions, as in there are multiple layers. Each layer is transforming some way or transforming your data in some form of the other, and they're stacked on top of each other. That's what deep neural networks are. That's why they have an unbounded set of neurons, as in there is no true structure, right? You can't ever say that for a given data, only ideally there should be certain number of neurons. No, there is no such thing. The number of neurons is unbounded, and so is the set of weighted interconnections between those neurons, which is the parameters or the weights, right? So it is unbounded. There is no bound to it. So there is no true architecture. But however, there can some of the tunable things that exist in deep networks are number of layers, number of hidden layers per number of hidden nodes per layer, number of convolution filters, number of attention heads in terms of text models, etc., or types of activation functions. All these are some things that can be changed in the structure of a deep model in such and we change them in such a way that somehow we are trying to approximate the distribution, the conditional distribution of the class label given the data, right? So that is all we are trying to do in deep model. And all of these things that can be changed or tuned are known as hyperparameters, right? Why are they called hyperparameters? Because the weights of the neurons or across the neurons are the actual parameters. And these things are parameters that lie above that, right? So they are hyperparameters. So these choice of hyperparameters are quite crucial because they can either lead to good approximation, they can lead to overfitting, which is like your model is well fitted to the training data, but it does badly on test data. Or it may lead to underfitting, where your model doesn't do anything at all, right? Or it can lead to more efficient or less efficient models. So now we need to worry about both the weights, which I denote by theta, and also the hyperparameters, which I denote by psi, right? So usually what happens is from the data, we train the theta, right? And but the shape or what the theta looks like, the size, or how your weight tensor looks like actually depends on what the hyperparameters are. For example, how many layers are there, what nodes are there, what is the size of your convolution filter, etc., etc. That will affect what your parameter space is or what your theta is, right? And till now, or till 2 years ago, these decisions of how those parameters will be tuned were taken by, again, machine learning experts. We used to sit down and decide how the layer should be, how many nodes should be there, etc. But that is not sustainable, given that so many devices and so many hardwares are coming up these days, right? So that's why what I'm proposing or what I'm trying to show you is that neural architecture search offers you a set of methods and techniques that will automatically tune these hyperparameters in some sense, using both the data as well as some input from ML experts or even domain experts, right? If you're not ML expert, for example, you are expert with cars, you know what a car computer should do, even though you don't know how they'll do it. So even if you're a domain expert, you can assign some of the values in the hyperparameters, right? So that is some level of expert input. And then there is data that is there. Using both of these things, NAS can automatically NAS can automatically alter your architecture, tune those hyperparameters in such a way that you have the most efficient or the most accurate architecture. So how is NAS done? Again, I showed you this picture previously, right? So in short, this is the optimization function. We are trying to do an argmax over the hyperparameters. Given that, what are you doing an argmax over? It is the quality. The quality can be judged in many ways. I'll say just now is the quality of the architecture that is there, which has been trained as well. So the quality of the final transformation function after training. And we are doing an argmax over the hyperparameter space. So that is the optimization function. And there are three main modules of any NAS method. Well, this will help us to understand the later parts, the case study. So remember this. There are three modules. The search space, which is basically the different kinds of hyperparameters that you will tune, right? That you need to tune, and that is dependent on your task or your hardware, etc. Right? So some methods design this search space as a naive vector of different kinds of hyperparameters. And some methods design it as cells or blocks. What are cells or blocks? As in, like, if you club things together. For example, you say that I'll have a convolution layer and a batch norm layer and an activation function such as ReLU, right? I club them together, and I think of it as one option. And then I have a bigger convolution layer, say 7 cross 7. Now this one was 3 cross 3. I have a bigger convolution layer, 7 cross 7. And I club with a batch norm layer. I club with a activation function ReLU. And then I consider it as another cell or block, right? So this is another choice. So we can think of search spaces like that as well. And there is another important module is performance estimation. How exactly, what kind of quality measures are important for you? That is important, right? So that is important for you to understand whether the current candidate in the current iteration is a good candidate or not. And finally, search strategy. Search strategy affects how fast you can actually end up in finding a good architecture. So these are the three things. And there are different kinds of search strategies. I'll not go into detail, but remember that there are 4 types: Bayesian optimization, gradient based, reinforcement learning based, and evolutionary systems. We'll touch upon reinforcement learning based search strategies today in our explanation for the later case study, right? So that's the end of what NAS is in general. Next is the case study, but I'll take a break of say 2 minutes and ask you people to answer or ask me any question you like, or have some water or whatever, right? Because I'll have water as well. Yeah, so yeah, we'll halt for 2 minutes.
Yeah, participants are requested to ask any doubts, please. Or they may take some water or.
Yeah. Please bring your coffee or water. I know this is a long session. Yeah, one more thing is that I know this is looking like information heavy, but what I want to convey is that there are many methods for making models optimal for deploying on embedded devices. But we are focusing on one of those methods, which is NAS, which I have particularly personally worked on in much detail, and also that it is kind of popular in these days, both in the industry and academia, right? For building embedded AI models. And we'll see what is required for NAS to work for embedded AI. And also that later when we will wind up, we'll try to touch upon some important points so that even if there is too much information in these slides and you have already forgotten everything by now, we'll remember some of the important points that are key takeaway from this talk. So yeah, I think are we done with 2 minutes? I'll just give a few more seconds. Okay. Okay, so I don't think anybody had any question yet. I'll wait for the Q&A session later. Anyway, so NAS for embedded AI. Why is this a case study? Because I showed you how NAS works, why NAS should be done, or what is the advantage of doing NAS, etc. Right? But doing NAS for finding models that are suited for embedded AI, there are some important considerations that we have to make. And I'll show you what those are. So that will be the central point of this case study. So that, like, if any of you are interested in building models for mobile phones or for mobile devices, and you want to use NAS in order to, instead of worrying about how to optimize, then I guess you can remember these things that I'll show you. Okay, before moving on to what NAS for embedded AI is all about, let us rewind to what are the important things. One is how to evaluate the candidates, right? Evaluation of a candidate is something that I told you is important. So in case of embedded AI, what is important? Is accuracy important? As in like accuracy of prediction, whether you can truly predict a cat to be a cat and a dog to be a dog, right? If is that more important? If of course it is important. I mean, if your phone, for example, if your phone, as I showed you, you clicked a picture of a shoe and your phone takes you to the government PF website, right? Provident Fund website, instead of taking you to Amazon, you will not be happy, right? So effective prediction is important. Accuracy is important. But in order to even make those models work in your phone, efficiency is also important. So we'll see how to evaluate efficiency. So and then another point is how to design a good hyperparameter space, or how to design a good search space. Like for example, do we always select like smaller smaller channel width, or smaller number of less number of channels because we are deploying on phones? For example, we limit that we'll only select between 2 and 7 or 2 and 5, between 2 and 5, right? The number of channels. But it may suffer in predictive accuracy if the channel is not 7 or not 6, right? So those are some important considerations. And finally, does search strategy matter? Yes, it will matter, and we'll show how, right? So this is NAS for embedded AI. So this is a NAS loop, just as I showed you. There is some kind of NAS, something that is called a controller. Controller is basically taking care of sampling or choosing from your search space and making a decision, and then continuing the search strategy, right? Trainer module is something that trains or adjusts the weights of your candidate. So only choosing the architecture is not enough, right? In order to evaluate whether that architecture is correct or not, you need to train the weights as well, right? So then comes your trainer. And since you're working with mobile devices, there would be other quality metrics as well, right? Just as I showed you, right? Then there is some kind of a feedback, and that feedback goes back to the controller. So this is NAS for embedded AI, and these bunch of mobile devices can be anything. It can be IoT devices, it can be phones, TVs, smartwatches, etc. So we'll look at NAS for embedded AI from the perspective of these three dimensions that I talked about a few minutes ago: performance evaluation, search space, and search strategy. So coming to performance evaluation. So as you can see, right, from this diagram, we are interested in not just accuracy. We're interested in a bunch of other things. For example, we'll come to these examples in a minute. So now what happens is that now just one number as a one scalar feedback is not enough. Previously we were happy that, okay, accuracy, we'll just measure the accuracy as the quality measure, and we'll see whether the quality is being maximized or minimized, and then we'll update in that way. That we were happy with that, right? But then now, due to NAS for I have shortened it to NAS for EAI, right? There's no space. Anyway, so now the optimization problem becomes argmax over all these different quality measures, right? And this particular plus with a round symbol, I have just overused it. I have done operator overloading, if you want to use that term. So this operator does not mean the usual mathematical thing that it means. Here it just means a combination operator, any kind of combination. It can be additive combination, it can be multiplicative combination, whatever, right? So some kind of combination. So you combine the qualities in some way, and you do an argmax over the search space, which is the architectural or which is the hyperparameters or architectural parameters. We also call it architectural parameters. So accuracy is a good quality score. We know that. It's great for measuring predictive performance. But just before going into something else, let us also consider if there are other tasks, right? For example, if there is image segmentation. As I said, image segmentation is finding out regions in an image, right? For example, if this region contains a human, or if there is a separate region in this image. For example, you have an image of a road, so the bus on the road will be a separate region. The footpath on the road will be a separate region, right? So if you want to segment that image in such a way, then accuracy is not a measure that you can use, right? Accuracy is just true prediction versus false prediction, right? So true prediction versus true label, right? Then there is something called IOU. So IOU is used to measure segmentation, right? Sorry, my bad. Yeah. So coming to the other hardware related qualities, right? So as we told, so hardware now chipsets are embedded. So the hardware is constrained. The resources in the hardware are constrained. So how do we measure quality in that case? So quality here is, we call it behavior quality, because how we want to say how your candidate architecture that you have found in this iteration I behaves on the given hardware. For example, you are trying to build a model for, say, some Google, Google or Samsung Note 10, for example, right? So you are trying to build a model for deploying on Samsung Note 10. So Samsung Note 10 has a certain kind of hardware. It has certain number of GPUs. It has certain number of CPUs. It has certain amount of memory bandwidth, etc. So given that hardware, you are trying to evaluate how that candidate will behave once you put that candidate on the phone. So that for example, latency is one such behavior quality measure. There could be other things like power consumption, memory throughput, as I have mentioned earlier. So which quality is important in case of embedded AI? Predictive performance is important, as we already know. But again, the model won't even run if it consumes more memory than can be allotted, or if the inference latency is so much that the user experience or the user can't even get the process done in a matter of seconds, right? Or not even seconds, milliseconds. Like if you have to wait for 2 minutes for your optimizer to work, for your scene optimizer to work, you will give up taking photos. So that's one thing. And secondly, sorry, not secondly. So we can understand that in most embedded AI cases, behavior quality measures are very, very important, right? Even in small IoT devices, memory is super important because you can't just deploy a large model. So memory is super important. Now, the final questions that comes to our mind is that how to even measure these qualities, right? How to even measure these? Can we think of a naive algorithm? For example, at every iteration, you take a candidate, load it into a device, run that candidate architecture on that device, and get your latency measure directly, get your memory requirement directly from the device, and then use that measure to accept or discard that architecture. And then when all this finishes, you'll get an optimal architecture. Is that doable? No, no way, because for every iteration, if you load that model into a device and get the feedback, it will your search will never finish. So that's one thing. Secondly, like some cases, people use some kind of proxies, such as flops, right? Flops will give you some measure of how big your model is or how complex your model is, but that's not always correct. So what people are moving towards is secondary prediction models, as in they're building secondary machine learning models, which given your architecture and given the type of hardware can predict what the estimated latency would be, what the estimated memory consumption would be, etc. So there are many work on that, including some work that I was a part of, and it's under review at one of the conferences right now. So moving on to, I'm just rushing through this part because I think we are to the organizers, how much time do you have left? Can you tell me?
So still we have 30 minutes. So.
Oh, still we have 30 minutes. Okay, okay, cool. Then there is one more thing I'll say. Is that no, but so I want to keep some time for Q&A if people are interested.
Yes, sir, then you can wind up in 15 minutes.
15 minutes.
15 minutes, right? Okay, cool. So yeah, so moving on to search space. So again, the other dimension is search space, as I just told you, right? Search space is important um, because we might think, why won't a giant search space work where we consider every kind of neural choices, we consider every kind of activation function, we consider all possible sizes of convolution filters up to a certain limit, of course. We consider all types of layers, such as convolution layers or attention layers or something, right? So if we consider all of these types together and we build a giant search space, won't that work? No, that won't work, because the search time would be huge. Like your search algorithm to actually explore through that entire search space in order to find the right choices would be like unreal, right? And your hello.
Yes, sir. Carry on, sir.
Yeah, please go ahead, sir.
Yeah, can you see my screen?
Yeah.
I lost connection for a minute.
It is visible, sir.
Okay. So yeah, so the controller, yeah, as I was saying, the controller may never even end up finding a good architecture. Then there is something called sparsity of feedback, as in you search through that giant search space. You come up with candidate architectures. That those architectures may not be too different from the architecture you found like 5 steps ago, right? So you are not getting the correct feedback that you're supposed to get, right? And then finally, the search space, the huge search space that you design may not even, no matter how huge that is, it may not even contain the correct set of hyperparameters that you actually need for your task, that you actually need for your hardware. Right? So what do people do? Sorry, it's stuck. Hold on. Okay. Sorry. Yeah, can you see my screen now again?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Yeah. So moving on to the next slide. So what are the how to choose the search space in some sense, or what in the industry, what do we do, right? So either we go for standard search spaces. So there is something, if you search on Google, you'll find these. There is something called NAS benches or NAS bench, right? NAS bench 101, NAS bench 201, NAS bench 301 and stuff, right? So what are these? These are basically people have sat down, researchers have sat down. They have evaluated different things. They have looked at different kinds of architectures that exist today. They have looked at important neural elements that are important, for example, in case of image classification. So you have choices in NAS bench for image classification or segmentation or whatever. So according to those choices, those standardized search spaces give you a search space that are most supposedly most ideal, right? And what is the other way? Other way is using backbone architectures. So what are backbone architectures? For example, you are doing a particular task. For example, you are interested in image segmentation, or you are interested in image enhancement. For example, scene optimization, right? So in such cases, we already know that some expert designed architectures already exist. For example, for image classification, MobileNet V2 has been found to work quite well. Not great, but quite well, right? So we know that that architecture exists. So we use that architecture in order to extract neural elements from that, right? So example, what kinds of or what sizes of convolution filters are great. For example, it should be multiples of 3, 5, or like 7 at most, right? Or for example, how many skip connections should be there, if there should be skip connections. For example, there should be, because you don't want to fall into the trap of vanishing gradients and stuff, right? So these things we can see from an architecture that already people have worked with, and we can tease out some of the neural elements and we can use those elements to design a search space in such a way that the search space is not just limited, but it's expected to contain some of the best or some of the most ideal elements that should be there. Right? There are some other examples as well. I'm not going through all the examples. You can just read through them. If required, I can even share the slide if the organizers want. Yeah. So okay. So we'll see later what the, and one more thing I just said before, that this NAS frameworks are dependent on both data in order to optimize the architecture, as well as they're dependent on some meager level of human input. So you can understand, right? Choosing neural elements from backbone architectures is a little bit of human input in some sense. Yeah. So so moving on to search strategy, I showed you like 4 strategies back then, right? So what each strategy is all about, like what are the pros and cons of each, right? So for example, gradient or differentiable search strategies, for example, they're good in continuous domains. For example, if you're using only numbers in your search space, for example, size of channel width, or size of convolution filters. So if you're using only numbers in your hyperparameter space, then they're continuous, so they're differentiable, or at least they can be made continuous and differentiable. But they work very badly on discrete or hybrid search spaces, right? Evolutionary search spaces, which uses genetic algorithms in some sense in order to search through the space of architectures. So they are good. They are good with powerful combinatorial search, and they're good with, as I said, multi-objective functions, as in where number of many quality measures are there, right? But they have a very high search time because they're, as you know, genetic algorithms are in general slow, right? Then there is reinforcement learning. Reinforcement learning is unlike genetic algorithms which work on discrete search spaces. Reinforcement learning algorithms can work with discrete as well as hybrid search spaces, as in discrete plus continuous, right? And the search complexity is controllable as well, as in like it is not as slow as evolutionary algorithms. And finally, there's Bayesian methods, which uses priors and posteriors if you have prior knowledge of which architectural elements are important. Right? So the question remains as to which method should we choose, right? So before making that choice, we have to understand that what is involved here, like what are the factors that we should look at. One thing is that embedded AI, the search space is definitely hybrid. It's not continuous, because in most cases we design the search space as cells and blocks. So that makes it makes the search space more tractable, more smaller, as well as it makes it discrete, right? So what are cells or blocks? For example, as I told you, one cell block can contain 3x3 filter. One cell block can contain 5x5 filter. So now we are not just looking at number or the size of the size of the convolution filter. We are making it discrete choices, as in cell type A, cell type B, cell type C, or something like that. So that's one thing. Secondly, there are categorical variables. For example, choice of activation, whether to use ReLU or whether to use sigmoid, or whether to use like max out, 10H, whatever, right? So that choice becomes a categorical choice. And there is another factor. For example, if you pose the entire search space as a differentiable, as a vector, right, in order to be used in differentiable algorithms, then it becomes intractable, because like there can be too many numerical choices. And if you pose it as cell blocks, then it's not differentiable, and gradient-based methods cannot work. You have to work with methods that work in discrete or hybrid spaces. Okay? And finally, multi-objective. Like as we have seen that we have to deal with many kinds of quality measures, such as accuracy, latency, power. Right? So that's why we need to choose algorithms that are well to do in multi-objective space. So let us look at two different ones. As we can see, our choice narrows down now. First is evolutionary. They're good with multi-objective problems because they're combinatorial in nature. They're good with discrete spaces because like basically genetic algorithms are like discrete elements of a population. Then you do mutation and combination and stuff, and then you get a new offspring, right? That's what evolutionary algorithms are. That's why the search space is discrete there. So they're very good with these two. What is the downside? The search time. So that will affect the production cycle. I'll show you. Production cycles are usually very short in the industry. So that's why genetic algorithms can create problems. Moving to RL, which is reinforcement learning. They are very good with sequential decision making. Sequential decision making is when you make decisions in a sequence, like you take decision, then there is a state machine, there is a state change that occurs, then you get feedback, and then the change state and the feedback, you make a judgment on what to do next, and you take another action. So that is reinforcement learning, right? So they're very good with hybrid and discrete spaces. Their search times are controllable, including using different kinds of exploration strategies. And there is a slight concern because multi-objective scenario, in a multi-objective scenario, RL is an open area of research, but there are methods which actually work with multi-objective RL. Right? Some methods do a simple weighted combination of different kinds of rewards. Right? So that feedback as I said, the feedback comes to the reinforcement learning algorithm. Right? When an action is taken on a state, there is a feedback. Right? That feedback is called reward in reinforcement learning. And in our case, these rewards are basically those quality measures. For example, your action is basically a new architecture, new candidate architecture, and you have quality measures for that new candidate architecture, and those quality measures are your reward functions. So, and in a multi-objective RL, in many naive methods, they combine using these weighted linear combination. Right? There are some more intelligent methods of combination. One of them is something that we have worked on that's still under review. So we'll not discuss that in detail, but know it in your heart that there are more intelligent methods to combine different quality measures. Sorry. So what happens like, so your final goal is, so you can see that reinforcement learning is kind of trumps over evolutionary strategies in case of industrial level NAS for building embedded AI. So before moving on to the final few slides that we have, let's look at one of the methods that had become popular like one or 1.5 years ago. It's called proxyless NAS, right? What happens here is that you don't have to go into detail, but look at this learnable block, as I was saying, right? So now learnable blocks are these 3x3 convolution, pooling, identity, etc. So these are regarded as blocks instead of continuous measures, right? So this is your search space, and you can see, right, there are two kinds of losses. So this particular loss contains accuracy, and then there is another component which is latency, which is the second quality measure. So they use latency and accuracy. They don't use any more thing, but as I showed you, that as I told you earlier, that some methods now have moved towards secondary predictive models. So they use this regression lookup model, as you can see in the corner, right? So regression lookup model is a secondary predictive model that predicts, given certain features of your new candidate architecture and the hardware that you're using, what is the estimated latency? And that is used inside the full loss function or the full optimization function. And they use a very early, very old reinforcement learning method, which is still popular. Don't think that it doesn't work. It works. So they use this reinforcement learning method. So this is one of the papers that is easy to understand. You guys can read it if you're interested. So it's from MIT Labs actually. It's published in ICLR 2019. It's called proxyless NAS. And as you can see in the results, they design different kinds of models for different kinds of CPU, different kinds of processing units. For example, if you have GPUs, they'll design a certain architecture. If you're running on mobiles, your architecture, as you can see, changes. It has like much smaller filters in some sense most of the time, but it's much longer. It becomes the longer architecture. Anyway, so this was to wind up. So this is to motivate you to actually like the notion of NAS. I have shown you these two plots. As you can see, MNASnet is a precursor to proxyless NAS. So MNASnet is something that that also works on building. Yeah, hello. Yeah, okay. So MNASnet is something that also works with building mobile models for mobiles, right? So you can see that with much less latency, it is able to achieve much higher accuracy instead of some expert design models like MobileNet V2. Here you see Google's EfficientNet, right? So Google has come up with this EfficientNet B7, B6. All these are versions of EfficientNet. So you can see that it also achieves much higher accuracy with much less parameters than some of the existing models, right? So EfficientNet is also designed with NAS. It's not designed designed manually or by hand. So this should kind of inspire us to look at NAS in a different light as a solution towards building lighter, more efficient models for embedded AI. Right? So we are coming towards the end of our lecture. There are a few more slides left. So I just want to reiterate here. So I understand that this could be too much information in all these slides, but so that you can go back home with the understanding of some of the popular choices in the industry in terms of NAS, NAS for AI, NAS for EAI. They look at this diagram. So in case of search space in the industry, we are a fan of using backbone architectures, and these are the reasons. In case of performance evaluation, we do a multi-objective performance evaluation, and we use secondary prediction models, which can predict estimated quality measures instead of actually running on the device, right? And as a search strategy across the industry, we usually end up adopting reinforcement learning, and some of the reasons I have outlined earlier as well. So you can go back home and have a nice sleep, thinking that you actually have an idea of what happens in the industry, which is basically hard to understand. I have taken much time to figure out. And to visualize this whole thing together. So this is, for example, a reinforcement learning loop, right? This is an agent. An agent takes an action in an environment, then it gets back a current state and the reward, and it takes an action again. This is reinforcement learning. And for NAS for AI, this is what happens, right? So the reward is now basically many rewards combined together, and then the state is basically your current architecture. And then you have a system that learns a secondary prediction model, which gives you latency, power, memory, etc. And also you can run the candidate architecture and get accuracy. So that becomes your combined multi-objective reward. And then you have some expert which helps you in designing a good search space, which is then fed into the agent. This is what happens in the industry, hands down. And finally, at the end of many iterations and many GPU hours, you get some optimal architecture. So I'll not go into detail of this slide. This is basically, I wanted to flash this slide that there is some work that works on designing optimal deep learning architectures and programmable processing units such as FPGAs together, as in like something that is suitable, the FPGA that is suitable for a model, as well as a model that is suitable for that FPGA. So it's like a combination that is learned together. So that's an interesting work that is going on in the field. So winding up, so we have 2 more slides, and then we can all breathe a sigh of relief. So winding up, what we want to look at, our key takeaways today, is that there is a big paradigm shift in the world. World is moving towards edge AI because of different reasons, including privacy, reliability, network bandwidth, the applications that you actually want to run on the devices that has the demand for example, that has to be done on the device. It cannot wait for that kind of latency, etc. Right? Then there are then the next point is there are many challenges to making deep. Oh, one thing is that many of these vision or speech or audio or video use cases or applications that people are interested in mobile devices or IoT devices or smart watches, etc. They are moving towards deep models, right? Though I think it's my own thinking that even shallow models can do a good job.
लेकिन समय शर्मा नहीं मानता सर, आप कुछ भी करो।
Sorry. Anyway, so yeah, so but there are many challenges in making deep models work efficiently.
ये है कि कॉलेज में भी इनकम बढ़ जाती है।
Can you mute for a second? I can't hear myself.
देखो ट्रेनिंग सेंटर एरिया कम से कम 3000 स्क्वायर फीट होना चाहिए है।
Hello, organizers, can you mute that person? I can't talk.
Yeah, did sir, did.
Okay, thanks a lot. Anyway, so yeah, so there are many challenges for making deep models run on embedded devices that we have seen. And to make deep models work on on-device efficient on-device inference, we need to look beyond accuracy. We need to optimize other things such as latency, memory requirement, power requirement. There are many methods that we have just flashed. We have gone through in very short that look at making models more optimal or compressing models in some way, such as quantization or pruning or etc. Or they alter the architecture in some way. Some look at compressing parameter space, some look at altering architecture. Then there is neural architecture search, which gives you an automated framework or platform to do all this together, right? To find out newer, more efficient architectures automatically and intelligently, given some input from the experts and the data that is available, right? NAS usually has 3 dimensions that you look at it from: search space, search strategy, and performance evaluation. And the case study on NAS for embedded AI showed us 2 things. One is there are some popular choices that exist in the industry with respect to 3 dimensions, as I showed you. For example, search space, in case of search space, usually people use a backbone. In search strategy, people usually use reinforcement learning, and performance evaluation is multi-objective, like they use latency, accuracy, and memory requirement, etc., etc. Right? And finally, yeah, so yeah, that's what I said. It's motivated from tractability and length of production cycle. Oh, length of production cycle. One thing I forgot to harp upon is that length of production cycle is also important. So if we go back to the, hold on, if we go back to the search strategy slide. So as you can see, length of production cycle, as I mentioned earlier, is important in deciding which search strategy to choose. Production cycles are usually very short, and search needs to complete fast, right? So finally, this is basically the last slide. So these are some of the scientific literature that can help you get started with this whole idea of efficient inference for embedded AI, right? There is a survey paper on NAS, and then there are different kinds of papers on NAS that you can look at. Basically, you search these keywords and you find the papers on Google. But most importantly, what I want to mention is that people who want to get started right away don't have to implement everything from scratch, right? All these platforms, open source platforms, are available that people can directly use. For example, Google's AutoML platform, which does NAS on cloud. There is Microsoft Neural Architecture Search Platform, or RKI, that does NAS on cloud. Then there is NNI and Qualcomm's Model Efficiency Toolkit that does not only NAS, but also has tools that you can use to do other things, such as quantization or pruning that I showed you, right? So those things are also available in the form of tools. So you can just explore and try learning or try understanding how those things work and how to design efficient models for resource-constrained devices. Thank you. That's the end of my talk. I'm open to questions, and I'll keep displaying this slide if you want to note down the links or something. Thank you.
Thank you, Dr. Mayukh Das. I request participants to please raise their queries they have. I request participants to please ask any doubts for their concern. Dr. Mayukh, I think there is no queries.
Okay.
Your slides were self-explanatory.
Okay, I'm glad to hear
Sir,
that.
excuse
Yeah,
me, sir.
please go
Sir,
ahead.
can you share me with us your mail ID? So in future, if you have any queries related to our research domains, we can take some help from your side. Can you
Sure,
share?
sure. I think Dr. Princey has my email ID, but I will share again anyway.
Okay, thank you, sir. And one thing more, sir, if you are new for this embedded system and still we want to start a research, I'm using the word start. So what thought of knowledge I need to acquire so that I can do some useful research in this using the AI in the embedded systems? What I can start from, where should I start with? As you have shared the resources thing, that is quite helpful. But what about these resources, what I need to do if I want to do something related to this embedded system with respect to the AI?
Okay, so so the thing is, so the easiest thing to do for anyone if they want to start off with is there are many blogs on Google, right? So so I don't know if you have, but I will send my slides to Dr. Princey or whoever is available. And you can look at the keywords and search for blog posts or blogs related to those topics, and that will give you enough idea. Like there are many blogs that people start off with, right? So as soon as you start off with, you'll start getting the idea of what these things are. And the main thing to remember about AI for embedded systems is that the main bottleneck is making the models more efficient, that they can be run on these resource constrained devices, right? Accuracy is okay, but if you can make your models more efficient, so that they run fast and they consume less memory, less power, but can reach the accuracy of the original model to some extent, to reasonably well, then you have a model for deploying on embedded systems, right? So my suggestion would be to start with such blogs using the keywords that you got from my talk. And secondly, look at the, I will share again. Yeah. Yeah. So look at these resources. Like if you start with these resources,
Yes, sir, I noticed this.
yeah. If you start with these resources, you'll get. So if you, for example, if you open up the page of NNI, right, and if you start reading the docs, it'll also redirect you to other resources, right? So
Right,
you can have one starting point, and then you can discover the others, and then you can read the survey on NAS.
and
That is one starting point that will redirect you to other points, right? So that's how you start.
okay, thank you so much, sir. Thank you.
Any other queries, please? Okay, now I request all the participants to please keep their camera on so that a group photo can be taken on the screen. I request all the participants to please keep their camera on so that their group photo can be taken.
So my system on the workplace does not have an embedded camera, so I will not be able to do the same.
Those who are able to do this can do. I request all the participants to please keep their camera on. Okay, thank you, Dr. Mayukh for sharing a very valuable information and which is related to the current topic. And definitely all the participants will take benefit of it. And you share the knowledge and discuss various domains of the artificial intelligence and machine learning that has been used to optimize the working of the mobiles and other applications. Thank you very much for to you. And
yeah, thank you. And do let me know if you need the slides. I'm open to sharing them if the participants need it.
Sure, sir. You please mail slides to Prince Randhawa. We'll take from there.
Okay. Thanks.
I also thank all the participants for sparing their valuable time and to join for this valuable talk. Thank you very much. Have a good day.
Thank you. Thank you for having me.